Next, we'll do like a 2D Laplace equation for the steady heat. Okay, this is also called the Laplace equation. First, we will talk about 2D Laplace equation in Cartesian coordinates. And so for the 2D heat equation here, our del square U will be 0. And this time we have the boundary condition for x and y. So here, when y is 0 and b, there will be 0. And for for x 0, there will be 0. For x equals the boundary A, there will be temperature T. So if we can plot like a plate here. So I have a boundary. This is B, this is A, this is X. And then the temperature here is 0, 0, 0, and here is T. And this is the right side view. The right side temperature. And you can see the temperature distribution like maybe this. This is the distribution of the temperature. And there's no initial conditions. But for the solution, we still guess and use the method of separation of variables. So we have x and y. Then we bring it back to our heat equation. And this time, instead of minus lambda square, we have plus lambda square, conventionally. Okay, then we have two differential equations, second order differential equations, y double prime plus lambda square y equals 0, and x double prime minus lambda square x equals 0. So now consider the first one. Again, that this will be the linear combination of your sine and cosine. Okay, so I have sine and cosine, and with the coefficient. And then we can bring the boundary conditions. The first boundary conditions. Then we have y of 0 equals 0, y over b equals 0. So y of 0 equals 0. Here is 0, 0. Sine 0 equals 0. So my c should be 0, right? So here is 0, and this one should be 0, so c should be 0. So the y is d times sine lambda y. So it's d sine lambda y, and then we can bring b to here. So sine lambda b should be 0. Therefore, lambda should be m pi over b. And n is from 1 to to infinity. Then the eigenvalues, lambda will be m pi over b. And the n is from 1 to infinity. Now I can write it down the y. That's dn psi m pi over b times y. This is the eigensolution. And then we can go back to x. So for x double prime minus the lambda will be m pi over b squared. X is 0. So in this case, your x n is coefficient times e to the m pi over bx plus the coefficient times e to the minus m pi over bx. Remember that we just used the 2 boundary conditions. We still have 2 more. So let's use the rest of 2. When x is 0 and a. When x is 0, then overall is 0. So x of 0 is 0. That means Cn tilde plus dn tilde, that's 0. And we can change the dn actually is just minus Cn tilde. And when we bring x as a here, and then we will get t. So here we have x of a times y of y. That's equal to t. That means x of a equals t. Any questions for this? No questions? Actually, something wrong. xa, this is a number, right? And this is a function. That'll be t. And then we can apply that actually x of a will be t. Correct? No. Because this time it's different. Okay. This one, because this is not 0, here it could be, well, this combination will be t, the multiplication will be t. For this y function, they may participate, some of them. Okay. So we cannot just say that, oh, because this is t, so x over a is t directly. Okay. In the past, similarly, these may change, but whatever they change, they should be 0. So it is better that we assume that this this derivative is 0. Then I really don't care about the value of t. But now the answer, the final result is not 0, it's t. So we cannot assume that this is t. Okay? So no. Therefore, we can just write it down our solution for x. So for x, there'll be Cn e to the m pi over b x, and the dn is minus Cn, so minus Cn delta e to the m pi, or minus m pi over b x. So we can rewrite this to sinh function, hyperbolic of sine, your n is from 1, 2, 3 to infinity. So my y is here, my x is here. The combination, this coefficient becomes an times hyperbolic sine and times sine function. Then one last step, we need to determine the coefficient an. So what is an? Remember that we have done. Did we use all the? Oh yeah, looks like we use all of the boundary conditions, but we can use this boundary condition again. So for an, we know that at x at a, here the temperature is, well, overall is T. So that means x is A. Okay, so overall for this boundary condition, and you can think about this part as your coefficient, say En, for example. So if I have a coefficient times sine, that's Fourier sine series. So to get this coefficient, so this is the coefficient, then the coefficient we have, how do I get this coefficient? Here. And I'll say this is boundary condition. And to get this coefficient, I need to T times the sine. Okay? And you can simplify it. The final solution is here. All right, and overall, this is the 2D Laplace equation in Cartesian coordinates. That means we also have Laplace, 2D Laplace in polar coordinate equation. If we have time, we'll go back to see this, but so far, let's just skip. And then we will talk about the wave equation first. So now let's see the wave equation. Here is the wave equation. Wave, like you vibrate the string. Okay, you vibrate the string, and the first, that is vibrating string with a 0 initial velocity. And here the y, this is y, function of y xt, that is the displacement function. Okay, if you like vibrate a string, they will go up and down, up and down. So this is the displacement for x. We have boundary conditions. At the boundary, it's 0. And then 0 initial velocity, that is for initial conditions. So here, this is 0 initial velocity. Okay, you take the derivative, the position becomes the velocity. And then the velocity is 0 initially at 0. So we still assume that my solution is the multiplication of your displacement plus times the time, and you bring it back to your PDE, the partial differential equation. Then you have this form. These two should be equal unless they are equal to a constant, a separable constant. And here, conventionally, we have a minus, so minus sign, so minus lambda squared. Therefore, for x double prime plus x squared x is 0. So immediately, we can say the x is a combination of cosine and sine. So cosine lambda x plus d sine lambda x. Let's just deal with this equation first. So now with the boundary conditions, so let's plug in. When I have a boundary conditions, x of 0 equals 0. So tell me that which coefficient is 0, or maybe two of them are not zeros. Is C 0 or D is 0? C 0, because 0 here, sine 0 is 0, right? So C cosine 0 is 0. Cosine 0 is 1, so C should be 0. So C is 0. And then the second boundary condition that gives you lambda n equals n pi over L. And n is from 1, 2, 3 to infinity. Because I put, well, C cosine, no, C is 0, D sine, lambda L equals 0. D cannot be 0, so only sine lambda L be 0. So lambda L should be n pi. That's why lambda is n pi over L. Now we can also see the equation for t, for the time. For t, or since we found that lambda equals n pi over L, so t double prime plus lambda square, a square lambda square, we have lambda square pi square a square divided by L square. T equals 0. And you again you can see that this is double in derivatives. So t should be the combination of your sine and cosine function. So that's half the Pn cosine lambda a, so there'll be n pi a over L x, and then your q times sine n pi a over L x. No, we have t, not x. Now we still have initial conditions. So first, let's see. we take the derivative, and then we have the zero initial velocity. So we take the derivative, and then set it to 0 when t equals 0. So if I take the derivative, cosine becomes sine. Sine becomes cosine. Sine 0, that's 0. And then cosine 0, that's 1. So I have to have Qn equals 0. Okay? That means my t is Pn cosine n pi a over L t. So overall, your solution becomes xn times tn. So it should be Cn sine m pi over L x times cosine n pi a over L t. And your n is from 1 to infinity. So the general solution, we get the linear combination. Okay, summation n from 1 to infinity. Now we need to determine our coefficient. So let's see what conditions we haven't used. Initial condition, this one. Okay, so y x 0, that's equal to f of x. So t is 0. When t is 0, here is 1. So I only have the summation Cn sine. It's like a Fourier sine series. M pi over L x. And n is from 1 to infinity. Therefore, the Cn, that's L 2 over L, and it integration from 0 to L f c sine m pi over L c. For example, if fx is sine function, if it is sine function, we can check n is 5. So n is 5, and you can find out that Cn is 8. So the solution of x is 8 sine 5 pi over L, and then cosine 5 pi 5 pi over L 80. Any questions for this? After seeing many examples, it looks like every time you just use the method of separation of variables and then bring this solution back to your differential equation, and you can have two equations. First, normally we will deal with the x first. So x will be the combination of sine and cosine. Determine the coefficient, which one could be 0, and the other one, okay, and then you get the lambda. You get the eigenvalue and also eigensolution. And then you consider the second differential equation about temperature or the time. and then you use the initial conditions to find the coefficients. And normally the coefficients, because you use the initial conditions, then you'll see that your function is a Fourier series, Fourier sine series, Fourier cosine series. So you can get the coefficients through the Fourier series or Fourier sine or cosine series. And then that's it. Okay. It's kind of like a procedure to find the solution. But every time you have a different type, so you have a different form of your boundary conditions and initial conditions. Like the next one is vibrating string with non-zero initial velocity. So here is initial velocity, not zero, so non-zero. Okay. So in this case, we know the boundary condition, initial condition. Our general solution, instead of sine and cosine, we will get sine and sine. Okay, you can practice doing the same thing. Here you will get sine function times sine function. And then to get the coefficient Bn, also using this initial condition. And for this initial condition, this is your overall coefficient for Fourier sine series. So this is your overall coefficient, n pi a over L Bn. To get these coefficients, you times the basis function. So 2 over L, integration from 0 to L, g cos c sine n pi over L cos c d cos c. Okay, during the weekend, try to find the general solution using the same steps. Okay. So now let's see, here we have zero initial velocity and non-zero initial velocity. We can also combine these two, because the other one at t equals 0, the time 0, that's we have a function, and here we have 0. So if I have non-zero initial velocity and also non-zero at time equals 0, what is the answer? The answer will be this answer plus this one, and doing the linear combination. Okay, so this is solution of equation 4 and 5. So this is another initial conditions. Right? Next one, if I have an equation for an infinite string, another type. This is the partial differential equation. Because it is infinite string, there's no boundary, so they will just like vibrating all the time. No boundary. So that means no boundary conditions. We only have initial conditions. And here you can see this is the zero initial condition, velocity. So 0, initial velocity, and then still using the methods of separations of variables and bring it back to this equation, you will get two ordinary differential equations. And for this two, you see this plus, you will get the x is the linear combination of sine and cosine function. And lambda is non-negative. And for the time, we also have t lambda, a linear combination of cosine and sine function. So here we have lambda at, coefficient, second term b lambda sine lambda at. Now let's use the initial condition, the zero initial velocity, to get, you take the derivative. So a lambda sine, b lambda cosine, and then t is 0. So sine is 0, that's 0. Cosine is 0, that's 1. So my bn should be 0, b lambda should be 0. So b lambda is 0. Then you have this term times cosine lambda at. In general solution, this is for particular lambda. So overall, lambda is non-negative. So I will do the integration from 0 to infinity. Then what is the coefficient c lambda and d lambda? For the coefficient c lambda and d lambda, we can use our initial condition, the other one. So when t equals 0, this is 0, so here is 1. So overall, it should be a function of x. And this is the Fourier integral. So for the Fourier integral coefficient, there we go. And if I change the initial condition, this is non-zero initial velocity. Then the solution cosine becomes sine. And then it's g of x. So g of x, when t equals 0, no, or they take the derivative, so here will be sine. Cosine. Cosine 0 will be 1. So g of x is the integration from 0 to infinity. Lambda a lambda cosine lambda x plus b lambda sine lambda x d lambda. Then your coefficient a lambda will be 1 over lambda a pi g times cosine lambda c d c, and then b lambda is 1 over lambda a pi integration g cos c sine cos c lambda cos c. Now let's continue for the non-homogeneous equations of your partial differential equation. So for non-homogeneous means that here I have a source term or external driving force. So for this heat equation, the wave equation, this one is a source term. Or we say the external driving force. We still have the boundary conditions and initial conditions, but now I just have additional term. So how do I deal with this additional term for the non-homogeneous equations? So this is like, as I said, the vibrations of a string driven by an external force. And we still use the separation of variables to find the solutions. So if I use a separation of variables, y equals x times t, position times time, and then we bring it back. And now you see that I still have additional term here. So to deal with this additional term ax, we can say that actually my solution is the yt plus the function of x. Kind of like changing variables, okay? Change the variables, then we can eliminate this external force, this external term. So if I have my solution, instead of just the separation of variables, we have y plus the function of x. Bring it back to the original differential equation. And then you will see y partial y square partial t square. And actually, we have these two additional terms now. A square alpha double prime, phi double prime plus ax. So we still have this term, then we want to get rid of that. So we can choose phi of x such that this term goes to 0. So we try to have a square phi double prime plus ax equals 0. So if I can choose this phi that is 0, then we have our familiar term expression, homogeneous one. Okay? So again, since we use the separation of variables, then we still have ax. For this ax, I want to get rid of this ax, so we just let our solution as y plus function of x. And then bring this solution back to our differential equation. Then I have additional two terms. And we'll let these additional two terms equal 0. Then I just have the wave equation for the infinite strings. not infinite string because we still have a boundaries, but just wave equations. And for the boundary conditions, with that x equals 0, so x equals 0, here is 0, here is 0. It should be 0. Okay? With that x equals L, so L, L, and L, also it should be 0. So in this case, we can choose phi of 0 equals 0, phi of L equals 0. So we choose the boundary conditions for the phi function. So phi of 0 is 0. And then phi of L equals 0. In that case, this y 0t will be equal to y lt. The boundary will be all 0. With these boundary conditions, and also these differential equations, for these two, we can get a solution for phi. So what is the solution for phi? The phi of x is equal to a divided by 6a squared times x and L squared minus x squared. So now we found the solution for phi. Let's deal with the y. Okay, for y we have these partial differential equations with the boundary conditions and also initial conditions. For the initial conditions, we need y of x0. X0 it should be 0. Okay, x0 should be 0. It should be 0. That means capital Y, this one is equal to minus phi because we have a y of x0. That means capital Y x0 plus phi 0, that's equal to 0, or phi over x. So that's why the capital Y at time 0 is minus phi x. And that is minus a divided by 6a squared x L minus x squared. How about the second one? The second initial conditions. Take the derivative. So for the second one, partial y over partial t equal to partial capital Y over partial t. So when you have t equals 0, it should be partial y x 0 partial t. That's 0. Okay, another initial condition. So we have the solution. The y equals capital Y plus the function of x, phi. You have 2al cubed over pi cube. Summation n from 1 to infinity. Minus 1 to the n cubed sine m pi x over L cosine m pi over L at plus a 6a squared x L squared minus x squared. Alright, that is the non-homogeneous equation. Next, let's see the non-homogeneous boundary conditions. In the past, we have boundary conditions like at the boundary, at least we have 1, 0, then it'll be easier to find a solution. But now, if I have the boundaries at 0, that's T1. At L, another boundary, I have T2. They are not 0. And we still have an initial condition. This is like the heat condition. So this is like a heat condition in a bar. But with ants, we have different temperatures. In this case, how do I solve the solution, find a solution? We still use the separation of variables. Okay, and then we will get these two equations. Now, with these two equations, for x, we use the boundary condition first. The boundary condition at 0 is T1. So at 0, it's T1. Then we can write it down, the x of 0 that's T1 divided by the function of t. And again, we have our solution. Instead of u with the separation of variables, we also add one more term, phi of x. And for this phi over x, bring this back to the partial differential equation. We have a phi double prime. And we need to choose the phi double prime equals 0. Then I still have the homogeneous differential equation. So phi double prime equals 0. Phi could be constant times x plus another constant. You see that actually if we apply the boundary conditions for x and we got this, and then we cannot continue. Not mentioned to like x over L. So that's why we say that my solution u is the capital U, but we plus the phi of x, just plus additional term. Okay, because why we need the additional term? Because here, if we try to find the boundary conditions, x at 0, that means 0 and 0, which means u of 0t plus phi of 0 equals T1. So in this case, we can set phi of 0 equals T1, which means u of 0, t equals 0. That is what we want. Similarly, we can also set the other boundary equals T2. Then the u of Lt will be also 0. That is our new boundary conditions for u. Remember that we find a solution for phi of x with these two additional terms like their boundary conditions. Based on that, then we can say this could be to satisfy the boundary conditions. There will be 1 over L T2 minus T1 x plus T1. Okay, so now we can deal with the U, the capital U, okay, with these boundary conditions. And we can also find the initial conditions. So to solve the capital U, let's see the initial condition. In the beginning, the initial condition is at 0, that's f of x. So the capital U at time equals 0, or the temperature is 0, it'll be U x 0 minus phi of x. So it's f of x minus phi over x. It's still a function of x. Therefore, your u will be 2 over L. N equals 1 to infinity. The coefficient. Minus phi of x. So phi of x is here. Times sine m pi cos c over L d cos c overall times sine m pi x over L. And times exponential minus n squared pi squared a squared t divided by L squared. And then you can find the original solution u plus the phi. Okay, so right now we just use one method that's called separation of variables to solve the partial differential equations. But for the partial differential equations, we have different boundary conditions or different initial conditions. Based on those conditions, you need to figure out in the process that how you finally find the solution. Okay, with the different boundary conditions, we have different tricks. And then later on, we mentioned that for non-homogeneous equations and non-homogeneous boundary conditions. And for those two situations, how do you find a solution? But remember, we have learned Laplace transform and also Fourier transform. And using the Laplace transform, Fourier transform, we can also find a solution. We just map the, for example, like time domain to the frequency domain or to another domain. And in that case, in that domain, probably it is easier to find a solution. And then you take the inverse Fourier transform or inverse Laplace transform. Then you get the solution directly. So you probably will avoid some tedious or some difficult part of dealing with this calculation. So let's see. For the Laplace transform, we can use Laplace transform to find the heat equation. Okay, so for example, this is our unsteady heat equation. We have a boundary condition. This boundary condition, we have a values between 0 and t naught. Otherwise, it is all 0. So we can rewrite this expression using the unit step function or Heaviside function. So that's B1 minus Heaviside function t minus t naught. Right. Remember the Heaviside function t minus t naught. I only have value when t is greater than t naught. And the value is 1. All right, and then initial condition here. So remember that the Laplace transform, here's the Laplace transform. F of t, your function times e to the minus st. This is the Laplace transform in time t. So when you take the Laplace transform with respect to t, okay, so here the time becomes the s domain. X is still the same. I only transform the time to s. Okay? So if I take the Laplace transform, I will do the both sides. Let's deal with both sides separately. Remember for the Laplace transform, the left-hand side it's s u x s minus u at t equals 0. This gives you s u x s minus a. So this is a. Now the right-hand side, let's just take the Laplace transform and see. Partial square u over partial x squared. That's the integration from 0 to infinity, e to the minus st, and your function, partial square u over partial x squared dt. This we can put outside here. So partial square over partial x squared and t from 0 to infinity e to the minus st u of x t dt. So what is this? The Laplace transform. So it's partial square over partial x square u of xs. Therefore, overall, the left hand side is s u of x s minus constant a. That will be equal to the right hand side alpha partial square u over partial x square. And the solution for u, the capital U, here we have a times exponential plus b times the exponential plus a over s. And you can check this solution is bounded when x goes to infinity. So the solution is bounded. That means this should be, the ASL should be 0. We only have the function of b of s. And then let's see the boundary conditions. For this boundary condition, we can bring it. Oh, we also need to take the Laplace transform because the t will go to s. So here we have the b is the constant or the magnitude times Laplace transform 1 minus the constant or magnitude times the Laplace transform of your unit size function shifted by t naught. Remember that every time if you shift in time, what happens in frequency domain or the S domain? You will have exponential there. That means your magnitude is still the same, but the phase is different. So here you have b over s minus b over s. And you shift, so you have a phase different. So overall, you have b minus a divided by s minus b over s e to the minus t naught s e to the minus square root of s over alpha x plus a over s. For this Laplace transform, we need to know for the inverse Laplace transform, this is called the complementary error function. So C means complementary. And ERF means error function. So that's called complementary error function. And actually, what is error function? So for error function, error function means 2 over square root of pi from integration from c to infinity, e to the minus c squared d c. Oh, sorry, this is the complementary. No wonder I just feel that where is it should be 0 to c. So this is the error complementary error function. And then for the error function, say E or F, that's 2 over square root of pi (0 to c) e to the minus c squared d c. So overall, you can see that the complementary error function is 1 minus error function. And the inverse Laplace transform of s over 1 of s will be 1. Let's just review the shifting theory. I have a Laplace transform, but if my function times exponential, that means in frequency domain, I will shift by a. Okay. If you think about this as a Fourier transform, when I do the modulation, then I will shift in frequency domain. Same thing if I times exponential, and then in Laplace transform, I will also shift. So if I shift in time domain, what happens in frequency domain? If I shift in time domain, in frequency domain or S domain, their magnitude is still the same, but the difference is just their phase. So they still have f of s times e to the minus as. So now once we have the u, we just have this u, right? We take the inverse Laplace transform, we can get our solution. So if I take the inverse Laplace transform, then we'll get our solution u. And you'll get a error function x over 2 times square root of alpha t minus b times complementary error function x divided by 2 times square root of alpha t. And then it will shift by t naught times the complementary error function. All right, let's see another method using the Fourier transform to find the solution. So here, the Fourier transform solution with the initial boundary value problems. Here, let's just have a review. The Fourier transform and then the inverse Fourier transform. And if I take the second derivative with, well, here the initial condition is 0, so that's why we have minus omega squared times the Fourier transform. And we have Fourier cosine transform and Fourier sine transform. Now, first, for the unsteady heat conduction in an infinite bar means that I don't have boundary conditions. I only have initial conditions here. So let's take the Fourier transform on both sides. So the left-hand side here. And then our solution will be the function of omega times the exponential. Now how can I get the coefficient? All right, so now let's try to find the A of omega. First, let's see the initial condition. If I take the Fourier transform, here we have Fourier transform. My x will become omega, so omega at 0. So that is just the Fourier transform of your f of x, right hand side. So left hand side equals right hand side. So when t equals 0, this is 1. So A omega will be equal to f of omega, the Fourier transform of your function. Okay. So the solution is the Fourier transform of your function f and times exponential. So when we take the inverse Fourier transform, we can get the solution. So let's take the inverse Fourier transform. To take the inverse Fourier transform, that'll be 2 pi u times exponential I omega x. And then we know that u of omega t here. And what is f omega? F omega, that's a Fourier transform of f of x, right? So we can also express this using the integration. So this is equal to 1 over 2 pi. This minus infinity to infinity is for omega. Okay, so I'll say omega from minus infinity to infinity. And then what is the f of omega? That's Fourier transform c from minus infinity to infinity. F of a c e to the minus I omega c d c, and e to the minus omega squared alpha t e to the I omega x d omega. So let's combine these two. So we will integrate with respect to c first. C is from minus infinity to infinity. F of a c e to the minus I omega, and here you have a c minus x. Okay, c minus x and exponential to the minus omega squared alpha t. This is d c. And then d omega. And you still need to simplify that. But you see that actually for my solution in frequency domain, I have f over omega times exponential. They are also omega. Or they are also a function. And you may think of this as two functions to do the multiplication. So multiplication in frequency domain, that means in time domain, they are doing the convolution. So we can also use the convolution theory. So two functions multiplied in frequency domain, in one domain. That means in another domain, they are doing the convolution. So we need to find their inverse Fourier transform first, then do the convolution. So first, let's find the g of x. So this will be g of omega. Okay, and then the inverse Fourier transform is this form, this expression. And then f of x, just f over x. Okay, so when I do the convolution, here's the convolution. So we flip x, we choose f to flip and shift. So that's overall here. All right, depending on what function f you have, and you can find the result later. The second one, unsteady heat conduction in semi-finite bar. In this case, we have the boundary condition now. And my x is from 0 to infinity, compared to here. This is minus infinity to infinity, because it's infinite bar. Here, semi-infinite bar, so x is from 0 to infinity. I have a one boundary condition and also the initial condition. We can use the Fourier sine transform. If we do the Fourier sine transform, we have partial over partial t. US for sine transform will be equal to minus alpha omega squared plus alpha omega u of 0t. And since our boundary condition, when x is 0, is 0, so this term goes to 0. So this term goes to 0 because the boundary condition. Then to solve this equation, that is a function of omega times exponential. There are also two functions. You can think about convolution later maybe. To find a omega, this function, we need to use the initial condition. So for the initial condition, if we take the Fourier sines transform, we have u x0, that should be u as omega 0, and then right hand side will be Fourier sine transform. So again, that if we have t equals 0, this is 1. So a omega equals your Fourier sine transform. So the solution will be e to the minus alpha omega squared t. And the inverse, you get u of xt be pi 2 over pi 0 to infinity Fourier sine transform e to the minus alpha omega squared t sine omega x d omega. For this Fourier sine transform, we can write omega is from 0 to infinity, and then the Fourier sine transform is the c from 0 to infinity f over c sine omega c d c times e to the power minus alpha omega squared t and psi omega x d omega. And depending on your f, and then you can continue. Here we skip another one, that two-dimension Laplace transform, well, Laplace in polar coordinate equation. So we still have time, we can talk about this. So this means that the 2D Laplace in polar coordinates, it is a steady state temperature in a disk rather than like in a bar. So in a disk, like this one, we have the radius r, and the theta. Now any radius just less than or within this plate. So del square u equals 0 means partial square u over partial r squared plus 1 over r partial u over partial r plus 1 over r squared partial squared u over partial theta squared. That is equal to 0. In the polar coordinate equation, then our boundary conditions are, and also initial condition, we only have boundary condition. It's a little bit different. For the solution, we still have the separation of variables. So we have the solution with r, the radius, and also the theta. Okay, and then we bring it back to the partial differential equation and we get this form. And still, we can separate these two dimensions, and then that will equal to a constant. So for these two differential equations, first for g, again, this g will be a combination of cosine and sine function. So g of theta is constant c times cosine lambda theta plus d times sine lambda theta. We can check that if we have n pi, so theta equals n pi, and also theta equals minus n pi, actually they are the same. So the lambda will be n, and n is equal to the r number, or natural numbers. Those are the eigenvalue. Then for the eigensolution, the base Cn cosine n theta plus Dn sine n theta, and n is the integer. For the r, we can tell you that the f n will be also a constant times r to the n plus a constant times r to the minus n. And we only consider the non-negative n. So r to the minus n, this term will give the unbounded solution. At r equals 0, so because it is in the denominator, so we can just let this coefficient dn equals 0. So this goes to 0. Then our general solution will be r to the n times the linear combination of your cosine and sine. And how do you find the an and bn? use your boundary condition. Finally, here we will apply that. For the boundary condition, okay, this is the Fourier series. So the A naught will be 1 over 2L minus L to L f of theta d theta will be 1 over 2 pi minus pi to pi and the coefficient here, this is the coefficient, okay, not just an. So this all around will be the coefficient.